Hello and welcome to this lecture of this module. We are discussing multiple random variable in this module, and so far what we have covered, that they are joint distribution, marginal distribution, and from last lecture we started that conditional probability distribution for the multiple random variables. And in last lecture what we have seen, we have understood the concept, and particularly with respect to the discrete random variable, and how we can get their conditional probabilities. We have discussed through a problem which is where the random variables are in discrete nature. We will continue the same concept, same conditional probability discussion on this conditional probability density, and this will continue for the continuous random variable from this lecture. So, basically we are continuing that the conditional probability distribution, which we will basically cover in this class for the continuous random variable, and we will discuss some problems where where we need to deal with the continuous random variable, that we will see. And after that we will go gradually to the discussion on different measures of association of different random variables. This is very important because when we are talking about that different random variables and we are considering their joint occurrence, their joint probabilistic behavior. So, basically we want to know their kind of association with each other, or sometimes if the number of random variables is more than 2, then we may interested to know that what is the association two random variables when the other random variables are either partialed out or taken care of. But basically, as you know from this last couple of lectures, that we are basically starting with the two random variables, which is the special case, which is known as the bivariate random variable. We will also discuss those measures in terms of the two random variables, and the similar concept can be taken forward for the more than two random variables. So, that will be our basically the I should not say that main goal, but one of the most important goal to understand the concept of multiple random variables. Okay, so, to start that we will first see that continuous random variable. In case of the continuous random variable, how we can get this conditional probability distribution. And as I told that this discrete bivariate random variable case means in case of this conditional probability distribution, that we have completed in this last lecture, and today we will continue with the same concept of conditional probability distribution, and we will know how we can determine this in case of the continuous random variable. Then also we will go with it with the joint distribution versus conditional distribution. This is in case of the both the cases, means discrete as well as continuous. Then the concept of independent random variable we will see in the light of this conditional probability distribution, and the some probabilistic condition we will see to declare two random variables to be independent. And after that gradually we will move to different measures of association among the random variables that we are dealing with so far in this module, through their moments, expectation, covariance, correlation. Maybe all these properties will not be covered in this lecture itself, but gradually this will be the overall outline how we will proceed one after another. So, we will continue now with this continuous bivariate random variable for the conditional probability distribution. So, if you recall from our last lecture, that this conditional probability distribution is we call it when the information of one random variable is known to us. For example, this is that distribution of y given x, and we have seen in the last lecture in case of the discrete random variable that this is the joint distribution. In case of discrete, it is PMF, that is joint PMF we have seen, and that divided by the marginal of the one random variable on which the distribution is conditioned on. So, here the as it is conditioned on the x, so we are using this fxx, which is nothing but the marginal probability distribution for x. So, in the last lecture we have seen that why we need this means this form actually makes it suitable. First of all, this conditional density is itself is a probability density. So, the properties that the common density function follows, it should be followed by this one also. So, the first one, you know that this should be non-negative, and second one, you know that this should be that summation over the entire support should be equals to 1. So, here the summation, if you want to know, then that you know that you have to do the integration over the entire range of the random variable concerned, and that should be equal to 1. So, basically that the pictorial representation that we gave in the last lecture, if we refer to that once again here on this writing pad, that this one, suppose that if we take that this is the two axes or the two random variable axes representing two random variables, and if we are having some kind of surface here. So, if this is a joint distribution of these two random variables, that means when we are talking about that this is conditioned on the x. So, that means this one, this particular value of this x I am just talking about. So, I am looking through if this has occurred. So, what is the distribution of y? Now, when we are talking that on condition of this, basically you are taking you are looking at the cross section, that cross section is passing through this value x. Now, that in case of the discrete also, we have seen in the last class that there are say depending on how many specific outcome that the x and y can have, and one example we have shown that the x can take the 4 specific outcome 1, 2, 3, 4, and y also can take 1, 2, 3 and 4. So, then for the condition on that x is equals to 2, then we have considered only in this column. So, this is for the discrete case, and similarly if I just take the same concept to the continuous random variable, that means I am considering a section of this joint PDF through this line, that where this x is given to you, which is equivalent to considering the one column. Now, you have also seen that if this is the marginal distribution of this of x, then you know this is the summation. So, first entry, second, third and fourth. So, these probabilities are summed up to get the marginal distribution at x equals to 2. So, and that one was taken and divided by these two, so that the summation of this all this probability is equals to 1. So, equivalently in this continuous case, what we will take that. So, this is the marginal distribution that at this section. So, whatever the section that I see here in this section, through this section, suppose that this is the section that I see through this one, through this x. Now, the total whatever the total means total, that whatever the distribution through this x, if that is divided by this joint distribution, then the final distribution that we will get, that will follow that the second property of a probability distribution function is that its integration over this range, over this entire range of this y should be equals to 1. So, this is the fact that we are taking that this fx, that is a marginal distribution of this of the random variable on which the distribution is conditioned on. So, the expression for the conditional distribution says that if f x y, this is a joint distribution, that divided by its marginal of the random variable on which it is conditioned, we will get the conditional distribution. So, this also we can represent if we want to know that just after some algebraic just take this one this side, then we get that the joint distribution of x and y is equals to probability of, I think from this equation you will get this expression directly, that is f the distribution of y on condition x, that is y given x multiplied with the marginal of x. Similarly, you can also if you see that if you just change this one, that is fx given y, then this will be the joint distribution, this will have no change because this is the joint distribution between x and y, but this marginal will change of instead of x it will be y, the marginal of y we have to consider. So, there also if we take the joint distribution will equate, then it will come that f x given y multiplied by the marginal of y, the random variable y. So, these two expressions are equal because both are equal to their joint distribution. Now, suppose that we are considering that the y given x. Now, if we want to know the cumulative distribution of that distribution of that conditional distribution y given x, then we have to do the integration of, because this is now this full expression is now the distribution for that conditional probability density, and so we have to integrate it from the left extreme to a specific value y with respect to y only, because we are talking about the y random variable y here to get the cumulative distribution function. We will take up one problem here which is on the storm event. The similar problem was taken earlier, but here we will specifically discuss about the conditional distribution, and we will see that how we can get that conditional and how it is how we can apply that whatever the conditional distribution we have obtained from this just now what we discussed. So, this problem is on a storm event which is occurring at a point, and it is characterized by two variables, and these two variables are one is the duration of the storm event, and second one is the intensity of the storm event, or we can say that this is a maximum in intensity. So, what happens in general that if we see the behavior of the storm event, then generally if the duration increases, the maximum intensity decreases. So, and vice versa. So, that there could be some probabilistic relationship between these two variables. Basically, these storm events are characterized by three variables along with this duration, maximum intensity as well as the total depth of rainfall. Say for example, if we see that one storm event which is lasting for 1 hour, then the maximum intensity, and on the other hand if we take the duration which is for 6 hours, then the maximum intensity, these two for the 6 hours maximum intensity will be lesser than the storm event of this 1 hour duration. As I told that these storm events are generally characterized by with also another random variable which is the total depth of rainfall, but here as we are discussing the bivariate case now, we are considering the two random variables, and so for a storm event we have considered only two random variable, two attributes, one is that its duration, another one is its maximum intensity. So, there are two random variables now, one is x and other one is y, and their joint distribution of this x and y is assumed to follow an exponential bivariate distribution which is given by this expression f x y. This is joint distribution which is equals to a plus c y multiplied by b plus c y minus c exponential minus a x minus b y minus c x y. This a, b, c are different constant, and that generally depends on the specific location, and this has to be determined. Here it is supplied that this A is equals to 0.06, B equals to 1.3 and C equals to 0.09. With these parameters, with the values of this constant, so our joint distribution is completely defined. Now, which is looked for is the find the conditional probability that a storm event lasting x equals to 4 hours, like so the duration is 4 hours, will exceed an average intensity of 3 millimeter per hour. So, here the unit of the intensity is millimeter per hour, and that x is your in hours. So, which is actually these constants are of course related to the units of this random variable that is being considered. So, now for the, as I just told, that if the duration increases, then the intensity will decrease. So, here question is that after giving this joint distribution, question is, so for the storm duration is x. So, now the conditional probability we should obtain on condition x, that is distribution of y on condition x. Now, condition of x is that x is equals to 4 hours. Now, then we have to determine what is the average intensity. So, the probability that the average intensity will exceed 3 millimeter per hour. This is the this is what we have to determine. To solve this one, first of all we have to obtain its conditional distribution, and you know that for to obtain this conditional distribution, we have to know its joint distribution as well as the marginal distribution of the random variable on which it is conditioned on. As we have seen that this is conditioned on the x, here x is the duration of this storm. So, we need to know the marginal density of x, and in the earlier lecture if you refer to, then from there you can see that for this type of distribution, the marginal distribution of the x is an exponential distribution, and it's with the parameter a. So, this f(x) is the marginal distribution of x is a exponential minus a x. So, this is the exponential distribution for the x. Now, once we know this marginal distribution, that means it is straightforward to get that their conditional distribution. It is just the division of this joint distribution which we know, and for its marginal distribution which is a e power minus x. So, we get the form of this distribution, that is conditional distribution, and of course, here what it is not mentioned here is that the both x and y, you know that for the exponential distribution support is from 0 to infinity. So, here as we are both this x and y are there. So, this support for this x and y both are from 0 to infinity. So, this is the complete description of this joint distribution of y given x. Now, we have to get its probability. So, we can directly do that integration, or what we can do, we can also get their cumulative density first, and cumulative density we have seen just from previous slide, that as it is that on the y on condition x. So, we have to do the integration from the left extreme to the specific value of y to get its CDF, that is a conditional CDF, conditional cumulative distribution function. So, at the left extreme is here 0. So, 0 to y, and this is the conditional distribution function. This we have to integrate with respect to y, and after this integration, and we have to follow some integration by parts or so, and you will see that it comes to the form of 1 minus a plus c y divided by a exponential minus b plus c x y. So, this is the cumulative this is the conditional cumulative distribution function for y given x. So, now I think just we have to put those values. Here we want to know that what is the exceedance probability of this y greater than 3 given that x is equals to 4, and you know that as it is given that y greater than 3. So, if we just deduct it from the total probability which is equals to 1, then it will be that y less than equals to 3 given x equals to 4. So, that means it is the f y x 3 given 4 means y less than equals to 3 given x equals to 4. So, we just put these values of y equals to 3 and x equals to 4 here with the other parameter that was defined, and we get the probability that it will exceed 3 millimeter per hour for a 4 hours duration storm is equals to 0.038. So, you see from this example that if we know the joint distribution and their corresponding marginal distribution, then this type of any such question can be answered. So, one question we have seen that what is the probability that it will exceed 3 millimeter per hour for a 4 hours storms, and we have seen that probability is very less. So, it will help to take a decision find. So, as the probability is very less, that is 0.038, then we can say that so getting more than 3 millimeter per hour may be very less probable. So, like this any of this type of answer we can get. But one thing that I was mentioned earlier also here is that if we know the marginal distribution for two random variables, then it is not that easy to know what is their joint distribution. Only one thing we can say from based on the theory is that if the joint distribution is your joint normal distribution or joint Gaussian distribution, then what we can say that their marginals also will be a normal distribution. But again that the reverse, that is the vice, we cannot say it is vice versa. So, that if I say that two random variables x and y both are having the marginal density of normal distribution x and y, we cannot say that the joint distribution what is that joint distribution. So, even though we are starting this type of problem that this joint distribution is given to us, getting the joint distribution from the marginals need not be very easy task. And in this module towards the end we will discuss about a recently or relatively newer concept in the civil engineering, which is known as copula. And this copula is generally one of the latest thing that is there to get their joint distribution, that we will discuss later. For the time being, we are starting, or whatever the problems we are describing that their joint distribution is known. So, so this is the question asked for, and we got this probability for this particular condition. Now, we will discuss about another important concept is called the independence, and in the light of this conditional distribution. So, first of all, if we just directly state what is how we can decide that whether two random variables are independent or not mathematically. There are two straightforward expressions are there, one for discrete and other one for the continuous. But before I go to that mathematical expression, if I just want to know what does this independence means, simply for the for two random variables, if we declare that the outcome of one random experiment doesn't have any influence on the outcome of the other one, then we can say that these two are independent. Now, to test this one mathematically, we have to take the help of their joint distribution as well as the marginal distribution, that is two random variables if it is available. It is not necessarily that two random variables only, we can say even more than two, that is if it is more than two or n numbers of random variables are available, then if we know their marginal distribution of this n random variables, and if we know their joint distribution as well, then the check is that whether the product of the marginal distribution is equal to their joint distribution. If this is true, then we can declare that this is independent. So that statement states that two random variables x and y are statistically independent if and only if their joint density PDF or PMF, of course PMF for the discrete, their joint density is the product of their marginal densities, that is Pxy joint PMF between x and y is equals to that Pxx marginal for x multiplied by Pyy marginal for the y, and this is for the discrete random variable. And for the continuous, the joint density PDF between x and y is equals to marginal density of x multiplied by marginal density of y. This is for the continuous random variable. Now, in the light of their that conditional distribution, there we will just see in a minute how we can get this expression. But in this slide, what I like to stress is that this is to declare it is statistically independent. This is this condition should be if and only if. So this phrase I want to stress, that is this is the condition. If it is satisfied, then only we can say that x and y are independent. Now, in the light of the conditional distribution that we discussed so far, if we see, that is we have told that the outcome of one random variable doesn't have any influence on the other. So that means here that there are, suppose this is for the discrete case, there are some two events. One is that x is equals to x specific outcome and y equals to y. These two are statistically independent, then obviously that probability that x given y should be equals to probability of that x, that is marginal of the x, because just now we know that the outcome of one have no influence on the outcome of the other. So the whenever we are telling that this x given y, so this given y have no influence on this joint distribution. That means that the probability of this x given y is equals to the probability of x, because this is have no influence of the outcome of the other, and vice versa, the probability of y given x is equals to the probability of y, that is the marginal of marginal density for y. And also from the conditional distribution, what we have seen that just few minutes back, that this joint density is equal to that conditional multiplied by the multiplied by its marginal. So this will be p, not f. P means we are using the notation p for the discrete random variable. So this condition multiplied by its marginal, so it is condition on y, so multiplied by the marginal of y, or the conditional density condition of x multiplied by its marginal density. Now, if we just replace this conditional probability with this what we have discussed just now, that is p x on condition y is equals to p x, or the p y on condition of x which is equals to p y, then all these expressions leads to that this joint density, that is p x y, is equals to their product of their marginals. So this is the this is in case of the discrete random variable, and similarly if we see that for the continuous case also the similar thing, only in case here we have to consider the PDF, not the PMF. So that PDF of this, that is x on condition y, it should be equals to its marginal, that is fx of x, and similarly f y given x, that is PDF of y given x, should be equals to PDF of y alone, because the outcome of this y does not have any influence from the outcome of x. So following again the similar concept, here also you can just write that this joint distribution we know that is equals to the conditional distribution multiplied by its marginal, and it is conditional y, so marginal is y here, and conditional x, if it is conditioned on x, that is given x, then it should be multiplied with the marginal of x. Now this conditional probability, if we replace from this their marginal itself, then both this expression will lead to that joint density, joint PDF is equals to the product of their marginal distribution, that is f(x)(x) multiplied by fy(y). So, these are the two conditions, one for the continuous, another for the discrete one, which should be satisfied, and if this is satisfied, then only we can say that this x and y are statistically independent. Now, we will take another problem on this continuous random variable, where we will discuss again the similar thing. Just the previous problem was based on this discrete random variable, and here we will take another problem on this water distribution system, and where that, and we will see that it's the probability of its failure. Just little background to this problem is that sometime for this water distribution system we use alternate path, and from the if everything is usual, then we determine that peak demand, and based on that this supply is determined, and of course the supply is determined with the various factors, that is its socioeconomic factor, water availability, and so lot of things are there. So, we determine, so this much water is available, and also that demand is also variable. You know that in during the peak hours the demand is more, and during the lean hours the demand is less. Now, when we can say that this system is working fine is that whenever the supply of the water is sufficient, or sufficient is the more than what is demand, then we say that system is working fine. But if the supply is less than the whatever the demand, then the system is declared as failure. Now, the failure of a system, the water distribution system, is also can have manifold reasons. One reason here that we have taken in this problem is that the sudden requirement of this closing of the path. So, sometimes there are some alternate routes are available, but these alternate routes generally having due to the various factor, we it is possible to supply only very less amount of water through the other path. So, this is also now that less amount of water, if it is during the peak hours, there is a chance that the required demand may not be supplied during the peak hours. So, that time the system generally fails. So, based on that of this, now there are so again that there are two different supply, where we can say that whether the which supply is available now, and again depending on the hourly demand also varies. So, for example, that from the peak hours also, say that morning 7 am to 8 am or 8 am to 9 am. So, what is the demand, and in this demand time, so there are, you can now imagine that this, if we consider these at the random variables, then the these random variables are also related to each other and dependent on each other before we can declare the before we can determine the probability of failure. So, one such example problem is taken here in the context of the conditional probability for the continuous random variable. So, the problem states the amount of water that can be supplied through two different routes of the water distribution system. So, among these two different routes, the first one is the usual route, and this through this first route the water can be supplied at a rate of say x1 unit per hour, and second through the second route the less amount of supply is possible, which is denoted as x2, and x2 is less than x1, which is also provided if, that is, the second route is used if the usual route is needed to be closed for the maintenance or any other reason. And the probability of facing such situation means here that I am using the alternate path, not the usual one. So, this situation, the probability of this situation is pi. So, whether the supply or the water is supplied to the community through the usual path or through some alternate path. So, the probability of supplying the water through the alternate path is pi, and obviously this will be less. Now, if the hourly demand denoted by y is met, then the system is considered to be working fine, otherwise it is failed. Now, once we are declaring that is the hourly demand, if we consider the two different hours, for example, here that two different times, one is the 7 am and the 8 am, which are considered to be the peak hours, is considered for two different random variables y1 and y2. Before that, this demand can follow a specific distribution, and it is declared that this distribution of this y, that is the demand, that is hourly demand, it follow a distribution that is lambda exponential lambda y for y greater than or equal to 2. You know that the support for this exponential distribution is 0 to infinity. Now, if we consider the two random variables here, that is y1 and y2, which represents the demand per hour during the peak hours commencing at 8 am and commencing at 7 am and 8 am, that means the 7 to 8 and 8 to 9 respectively, these two are the requirement. That demand is also varying. But anyway, we have considered that both the things are following. For the simplicity sake, we have assumed that both the demands following the same distributional form. One is that lambda e power minus lambda y, which is exponential. We could have even considered that two variables here is following two different type of distribution. Means the type of distribution can be kept same, that is exponential distribution, but this parameter can be changed, that is for the y1 it is lambda 1 and for the y2 it could have been lambda 2. But just for the demonstration purpose, here it is considered that both are following the same distribution. Now, let A represents that the failure of the system in this peak hours, that is the required amount of water is not supplied to meet the demands. Now, the question is, what is the probability of the event A, this T is a spelling mistake, event A. So, that during this peak hours, that means 7 to 8 and 8 to 9, these two time whatever the demand is, that is y1 and y2, this required supply is not there. That means that y1 is greater than either x1 or x2, whatever is being supplied, or that y2 is greater than that x1 or x2, whatever the supply during that time. So, we have to determine the failure of the system through this. Okay, to solve this one, the failure of the system can be written as like this. So, this is the A, that event we have declared, and so that means, as I told, that y1 should be greater than that x, that is the supply, which is, you know, that this supply here is this type of random variable is generally called the dichotomous. Dichotomous means it can take only two possible values. So, here we have seen that it can take only the two values, one is x1 and other one is x2. So, x1 is the usual supply and x2 is the supply through the alternate route. So, the failure means y1 should be greater than what is the supply, that y1 should be greater than x, or that y2 is greater than x. Now, the failure is also here, it is represented as 1 minus this y1 less than x and y2 less than equals to x, because of this the help from the cumulative density, the concept of the cumulative density, you know, that we need to know that less than equal to. So, we have just considered that this is 1 minus of this either that y1 less than equal to x and y2 less than equals to that supply x. Now, it is also known that so far as the distribution of this x is concerned, that is that I told that it is a dichotomous variable. So, it can take only two possible values, one is that x1 and another one is the x2. And in the problem, it is declared that probability of facing such situation, that such situation means when we are supplying the water through the alternative path, that is x2 is the supply. So, that probability is your pi, and so the probability of supplying that x1 amount, that is when x is equals to x1, obviously this would be 1 minus pi, because these two are the mutually exclusive events. So, either of these two should occur. So, if the probability of one event is pi, it should be that for the probability of the other one should be 1 minus pi. So, now this is the marginal, this is basically the marginal distribution of that x, and which is you can say that for these two different case. Now, using the conditional probability and considering the possible closure of one root between that 7 and 8 m, the above equation is can be expanded. There is a probability of failure, this thing can be expanded, that so 1 minus, as I just let once again refer to this one. So, 1 minus y1 less than x and y2 less than x. So, we are now expanding this term, that is y1 less than x, and we are also expanding that y2 less than x. How we are doing that is that the probability of y1, that is between 7 to 8, is less than x1, comma probability of y2 less than x1, because we are assuming both the time supply is usual, on condition that x is equals to x1, which is multiplied by its marginal. So, this is the conditional multiplied by its marginal, that is x is equals to x1. This and the other situation is the supply is x2, that is probability that y1 less than equals to x2 and y2 less than equals to x2, on condition that supply is x2, this multiplied, this full quantity multiplied by the what is the probability of x2. That means, this is the cumulative conditional distribution for this y1 y2 when this variable, when the supply is x1, and this is the cumulative distribution when the supply is x2. So, which is represented through this expression. So, this cumulative distribution multiplied by the marginal of that x for the value x1, and this cumulative multiplied by the marginal for the value x equals to x2. So, these two are obtained to and after that, if the available supply x is assumed to be independent of the y1 and y2. Here one thing I want to mention, that even though this is written here, it is not for the practical when we decide that what should be the supply for this one, there lot of analysis is done to determine that what should be the supply. But once we have decided that, now the what is meant here for the independent of the independent means the demand and supply are independent. What we meant that now the variable demand and the supply, these two variables are assumed to be independent. That means, I have decided from the analysis that this time the supply will be this much amount. Now, this one whether the distribution system needs the maintenance or not, so that is due to the sudden maintenance and this type of reason we need to change the supply. But the demand is always the whatever the requirement of the whatever the requirement of the community. So, that is why it is declared that if we assume that these two events are independent to each other, then how this expression is further simplified. So, that is why it is explained that if the available supply x, either x1 or x2, is assumed to be independent of that y1 and y2, thus it can be written that this y1 less than equals to x1, y2 less than equals to x2, that condition that x is equals to x1 is now omitted, which is multiplied by their marginal probability, that is probability x equals to x1. So, this is the cumulative distribution for this y1 y2, which is in case of this x1 it is multiplied by the marginal probability of x1, and the other one if it is x2 then it is multiplied by its marginal probability x2. Now, if we assume that this y1 and y2 are also independent, y1 and y2 independent means what is the demand during the 7 am to 8 am and the demand between the 8 am to 9 am. If these two demand are independent, then we can write that this cumulative distribution, that is for anything, that is for, if it is that, now it is explained here for the case of x1, is equals to probability of y1 less than x1 and probability y2 less than x2, and you know from the independence just now we discussed that. So, this is a joint distribution which should be equal to the their marginals, that is probability of y1 less than x1 multiplied by probability of y2 less than x2. So, that means these are the cumulative distribution for the y1 and y2. So, these cumulative distributions, these multiplications should give that cumulative distribution for the joint if this y1 and y2 are independent. So, this expression is now replaced in this form, and what we will get the probability of failure is that this. Okay. Now, again this cumulative distribution, when we say that probability of y x1 multiplied by y1 and y2, and in the problem also for the simplicity sake we assume that these two are following the same distribution, same exponential distribution. So, with the identical parameter as well. So, that is why here we are just expressing that this is to be squared. So, multiplied, instead of multiplying that f y1 x1 and f y2 x2. So, it is f y x1 square, and this the other one is that f y x2 square. Now, these two expressions are replaced in that expression for the probability of failure, which is equals to 1 minus f y x1 whole square multiplied by the probability of supplying x1 amount plus probability of y x2, that is the cumulative distribution of y for x2 square multiplied by the probability of supplying amount x2. Now, these two are known, that probability of x2 equals to pi and probability of x1 is equals to 1 minus pi. So, putting this expression we obtain that probability of A is equals to 1 minus pi multiplied by f y for x1 whole square plus this pi multiplied by f y for x2 square. Now, you know these cumulative distributions are for the this exponential distribution is also known, that is 1 minus okay. This will be you know that 1 minus e power minus lambda x. If this is the exponential density, then the cumulative density, you know, this will be 1 minus e power. So, this is a mistake, it should be, instead of lambda e power minus lambda x, it should be 1 minus e power minus lambda x. So, this should be the cumulative distribution, and the support is same, y greater than 0. So, this cumulative distribution should be placed here, that is 1 minus e power minus lambda x1, this is for the x1 value square, and 1 minus e power minus lambda x2, this power square. So, this whole quantity. Now, these parameters we know, as we have declared that we know the distribution. So, that means we know these parameters also, that means the lambda we know and this pi we know. So, if we know this parameter, we know that this what is the amount of water, that is the x1 and x2, their magnitude. So, with this magnitude we can calculate that what is the probability of this failure. So, as a system designer, so this type of probability we know that this type of probability should be minimized. So, once it is satisfied by the designer, the system designer, then that design can be accepted. So, here the basic idea is that after getting this probability, this probability should be minimized to the extent possible. Okay, so we have discussed so far the conditional probability and their practical application in some of the civil engineering problem we have seen, and also now what the next thing that we just was referring to in this at the starting of this lecture is that this, whenever we are talking about this multiple random variable, we are interested to know their joint association. Suppose that if we just start our discussion with this bivariate random variable only, that is the x and y, there are two random variables are there. Now, how they are associated with, I cannot say the related with, because that's that need not be the right word, but the association when we are referring to, that can be the linear association or the nonlinear association, or their variability with each other, the covariability between two random variables. All these things are important, and these things are also generally obtained from their probabilistic that their joint probabilistic behavior. So, this we will discuss now one after another, and we will go through this concept, that is, one is that moment, then the covariance, correlation, conditional mean, conditional variance, moment generating functions. Maybe all these things will not be covered in today's lecture, but we will just start with one after another, and we will know that what the important information that we can obtain from these measures for the multiple random variables. So, you also know that these moments and the expectations we have discussed in case of the single random variable, and obviously here also the similar concept will be used, but it has to be extended to the higher dimension. For the single random variable, what we have seen, that is just on one axis. If we just go for the pictorial representation based on the one axis, we have discussed their area concept, that is the moment. When we are discussing, we have discussed in the concept of the moment. Now, if we just extend it for the bivariate case, that means it is now a 3-dimensional space. So, two axis represents two random variable, and other one is the probability density. So, now if we suppose that the expectation, if we just extend to the 2-dimensional case, now whatever we have considered for the area in the 1-dimensional, that the single random variable, now the same thing for the 2-dimensional case, it will be the volume. Now, you can imagine, for if it is more than 2, then it is something going to be a 3-dimensional for 3 random variables, and 1 dimension for their probability density. So, it can be extended accordingly. So, anyway, to start with the bivariate case, we can just go for the first is that the fundamental properties and the measures that we have discussed for the random variables. These are applicable for the case of the multiple random variable also, and some additional properties and the measures are introduced here to discuss their joint variability of the two or more components of the random variables. So, as I was just telling that the fundamental concept that we have used earlier for the single random variable will also be applicable, and the same concept should be extended first to understand for the 2-dimensional case, and then we will go for the we will take that for the higher dimensional, at least that is for the mathematical expression purpose. So, this detailed discussion on these moments and its expectation, then one of the most important thing is covariance, and from the covariance we will know that the correlation is the measure of linear association. This linear is important. Then gradually we will go on the other properties as well for the multiple random variable, and this will be started discussing in the next lecture. Thank you.